All right, good morning. Chemists will get started now. I'll start off with a little demo to recap what we learned about last week about some of the scientific experiments that were done to kind of unlock all of the secrets of what we know as the atom today. So the idea that atoms are comprised of different subatomic particles, electrons, protons, and neutrons. But way back then, they didn't know what protons, electrons, and neutrons were, and so some experiments had to be done to discover them. So we looked at the J.J. Thomson CRT experiment, which discovered the existence of electrons, along with Millikan's oil droplet experiment that determined the charge of an electron. So those two things together determined both the mass and the charge of an electron, but we needed those two experiments together. And then our next experiment was Rutherford's gold foil experiment, where Rutherford shot alpha particles, so a type of radiation, at a very thin gold foil sheet. And so what crazy observation he made is that when he shot these alpha particles at that gold foil sheet, a small fraction of those alpha particles were deflected back into, basically back away from that gold foil sheet. That most of the alpha particles went straight through the sheet, but a small fraction went backwards. And so he deduced from that, hey, there is this very dense mass at the center of every atom, what we thought was atoms. We used to think they were like indivisible balls, like billiard balls like this. But now we've discovered the existence, the nuclear model of our atom, that, hey, we have this very dense nucleus at the center. An atom is mostly empty space except for that very dense mass in the center. And from the experiment, we deduced that that center is positively charged because alpha particles are positively charged. And so since they were deflected, that means repulsion was involved there. So this nucleus was positively charged. And we'll talk about the nucleus in a moment after this demonstration. So Rutherford used different types of radiation to shoot at this gold foil. So I just have some examples of some different radioactive sources. And so we can just see, you know, everything around us actually does emit a small amount of radioactivity. So, you know, any one of these different sources, alpha, beta, gamma rays, but just to differing extents. So here are just some samples I have. So left to right, I have salt, a different salt, potassium chloride, and then a uranium salt. So let's be quiet and listen at the different signals that these samples give. So I have a Geiger counter here that does beep, so we'll listen for it to kind of deduce the extent of the radiation that these samples give off. So here's my Geiger counter. So like I said, everything emits a small background amount of radiation. So now I have to learn how to shut up. If you listen closely, even just background radiation, you'll hear a couple clicks, beeps. So let's just be quiet. Do you hear it? Yeah, a little bit of beeping. All right, so tiny background beeps. So here's our first sample, sodium chloride. So you tell me, is it radioactive? Does it emit a lot of radioactivity? No, it doesn't. Okay, so that's salt, NaCl. So, you know, this is the table salt that's on your dining room table. Now here's a different sample, KCl, potassium chloride. So it's a little bit different. Come on. So you do hear it beep a little bit. So there's a little bit of radiation coming off this, probably a little bit more than the sodium chloride sample. And so KCl is important because I don't know if you've heard the wives' tale or the little tidbit of information that potassium is does have radioactive isotopes, like the potassium that you and I, the supplements that we take. There's a little bit of radioactive material there in that potassium atom. Now let's look at this sample. So this is a uranium compound, so it's going to be much different. Yes, that's much different. So that is a uranium sample. All right, so you might be wondering, why do I have this banana sitting here? All right, so I'll show you the sample of KCl again. All right, that's KCl. What do we know about bananas and potassium? High in potassium. So I'll now do the banana and you tell me if this makes sense. So this is the potassium sample. Now I will put it on the banana. Do you hear that? Does this make sense? This is the potassium sample. Here's my banana. So we said potassium is high, or bananas are high in potassium, but look, this Geiger counter is going off the charts. Why do we think this is? Do you think it's the banana that's giving off this signal that we hear right now? Is it the banana? What else is here on the banana? This plate, yeah, so it's actually the banana does not emit anything. Yes, it doesn't emit anything, okay? So I just tried to trick you, all right? Because there's like that wives' tale that potassium, is, too much bananas will give you radiation poisoning. It will not, all right? Bananas give off very, very little radiation, just like this pure salt we have. What's special is this plate, right? It's the plate that is emitting, all right? So this is a vintage piece of Fiesta ware that the glaze to make this is made with a uranium, basically uranium, or thorium or something like that. But there's a whole TikTok group out there where folks go thrifting for vintage Fiesta ware because of its radioactivity. So it's the plate that's radioactive, the banana is not radioactive. So sorry to ruin that for folks, but yeah, so it's the plate. All right, so there's that demo. I've been good in doing a demo a day. I'll do a demo, I'll blow something up on, or I'll do another fun demo on Thursday as well. All right, so let's move on from that experiment. I guarantee you there will be at least one exam question on those experiments, all right? And I mean a deep depth into those experiments, because talking to folks in office hours, folks have told me, yeah, I learned about, the oil droplet experiment, but I didn't understand, like in high school, but I didn't, get it. But we, ask questions on a deeper level, much like I lectured last week. So do keep that in mind. I do have those 2 practice exams already posted for your studies. All right, okay, so then we talked about the existence of the nucleus, and then I just kind of skipped over these 2 slides. Next, what was discovered was the proton after the electron, where proton's positively charged, and then last what was discovered of our subatomic particles was the neutron, and really it was just, this is a very sneaky subatomic particle because it has no charge, but it does have mass, but this was one of the last things to be discovered because neutrons have no charge. In all of the other experiments, we used electric fields, charges, attractions, repulsions to discover these particles. Neutrons don't have that, so it was the last thing to be discovered. All right. So on to new stuff, and that is now that we understand the nuclear model of our atom, we have the existence of protons, neutrons, and electrons. Let's look at how we communicate with scientists what type of atom we're talking about. So we're going to be using our periodic table and the information from that to look at our different symbols for our atomic symbols. So the piece of information that we should bring along from earlier in the chapter is that protons and electrons have charge, but it's only protons and neutrons that have mass, all right? So we got to bring that along. Protons, those are super important in our atomic view because that number of protons is actually the atomic number that comes off of the periodic table. So if you look at our periodic table, all of them have like a really large whole number associated with it, each element. That number is the number of protons in that element. So for example, carbon, all carbon atoms have 6 protons in its nucleus. So that's how we identify our different elements, where the atomic number is the number of protons that is related to the identity of that element, right? So remember, protons are positively charged. So if we're talking about a neutral atom, charge neutral, I mean, if carbon has 6 protons, in order for that atom to be charge neutral, 6 electrons also have to be present as well. But what we'll learn here is that not all atoms have to be charge neutral. So the idea here is that charge of an atom or particle is always related to the difference of protons and electrons in that atom. Remember, protons are positively charged, electrons are negatively charged. So we have to kind of add up those charges to see what's the overall charge of that particle. All right, Okay, so in Rutherford's, nuclear model, he says that the nucleus has all the mass in our atom, while the rest of the atom is empty space. So what we'll see in this nuclear model is that electrons live in this cloud on the majority of our atom in this cloud. That's kind of, they're whipping around the atom very, very fast. And at our center nucleus, this is where we have our protons and our neutrons in the center. That's the very, very dense nucleus that Rutherford was referring to before. And so when we want to communicate what is the mass, what is the composition of that nucleus, this is where we use the mass number. The mass number tells us the composition of that nucleus. Remember, the nucleus contains protons and neutrons, so we're just going to sum up those two numbers to give us the mass number, right? And so this is all the information we need to represent atoms using these isotopic symbols. So here are some different examples of isotope symbols, and from the information given, we can deduce, okay, how many protons, neutrons, and electrons are on this atom for all three of these different examples. So how we read this is that the number in the top left corner, this is our mass number, all right? The number on the bottom here, this is our atomic number. The atomic number, again, tells us the number of protons that are in our nucleus. And then if there is a charge, the charge will go in the top right corner, right? So that's how we read this symbol, right? So using these different equations that I've presented, the mass number equation, it's protons plus neutrons. The protons is related to the identity of the element, and the overall charge of the atom is related to protons minus electrons. We can figure out what are all of the subatomic particles present in this thing. So if we're looking at carbon, the number of protons in this atom is 6, because all carbon atoms have 6. And I've written that carbon, that 6 atomic number in the corner there. All right, so how can we deduce how many neutrons are here? Well, we can take the difference of the mass number and atomic number to get how many neutrons are there. 6 protons are present already. They're in the nucleus, so that means there has to be 6 neutrons as well, because 6 plus 6 equals 12. And then lastly, number of electrons. This is related to the charge. So the number of protons and electrons will be related to one another. This is a charge neutral element, so there are 6 electrons as well to equal out those protons. We can look at another isotopic symbol. So there's one symbol. Here's a different symbol. Notice that the mass number is different. That's the only thing that's different. Carbon is still carbon, so there is still 6 protons present here. But then how many neutrons are there? Just yell it out. 8, yes, 8, because the mass number is different. Remember, protons plus neutrons is your mass number. And then how many electrons? Just yell it out. 6, yes, because it's still charge neutral. Perfect. All right, so both of those first two examples, we call them isotopes. We call them isotopes because it's the same element, but they just have different number of neutrons. And this happens in nature, all right? Elements with different mass numbers, different number of neutrons, but notice that the number of protons are the same. And there's some other examples as well, isotopes of hydrogen. We have a regular hydrogen, we have deuterium, and we have tritium, which all of them have 1 proton, but just different numbers of neutrons, either 0, 1, or 2. So just like our carbon example. All right. Okay, so those two carbons, carbon 12, carbon 14, those are isotopes. So let's look at a different one. See, this one is actually an ion. So I just made something up for us where here is an example where the charge actually isn't 0. So we account for that via the electrons. So this is still a carbon atom. So we still have 6 protons. How many neutrons based upon the mass number? 6. But is there 6 electrons here? No. How many are there? 7. Yes, you need that extra electron to give that particle an overall -1 charge. So notice here when talking about ions, it's just the electron number that is changing. Because if I took, because you could think, oh, to make something negative, I could take away a positive charge, right? But if I take away a proton, is it still carbon? It is not. It's something else now. So that's the idea there, that charge related to protons and electrons, but don't change the number of protons because your identity of your thing will change. All right, so let's practice everything together. So I talked you through the process. These are the 3 equations you should just memorize, right? And it's just summarized on the previous slide. I just have them all together. This is how you can deduce the number of subatomic particles in any isotopic symbol. So protons related to your element identity, that's your atomic number. Mass number is related to protons plus neutrons. That's everything in your nucleus. And your charge is equal to the number of protons minus the number of electrons. Remember, protons are positively charged, electrons are negatively charged. So you might notice here in this first symbol I give you, I don't have the atomic number written. But do I really need to write the atomic number there for you to know how many protons there are? How else can you get the number of protons for this first symbol? Yeah, just use the periodic table. Look for AS. We don't even have to know what element that is, all right? It's arsenic. But if you look for AS, what atomic number does it have? 33, yeah. So when you see atomic symbols like this, you probably will not see the atomic number because 33 means arsenic. It means AS. So we don't need to actually write that one in the bottom corner. We already know that arsenic has 33 protons, all right? So to get neutrons, we use this second equation, the one that relates the mass numbers, okay, protons and neutrons. This is related to mass number. Someone do that math for me. How many neutrons are there? 40 what? 42, okay, good. So 33 plus 42 is 75. That adds up to your mass number. So 75 is the mass number. Here, I already tell you that the charge is 0 because there's nothing written there. If there's nothing written on the symbol, it implies that it's a 0 charge. So that means the number of electrons should be 33 because protons minus electrons will always be related to your charge. All right, got to equal them out. All right, next one, nickel. Nickel, so I say nickel 61, so that means its mass number is 61. I don't write the atomic number, but that's okay. I can just look it up. Nickel has how many protons? 28, great. All right, then how many neutrons? Okay, let's do that math. Okay, 61, stupid calculator. 61 minus 28 is 33. All right. The charge of this nickel is also charge neutral, so there should be the equal number of electrons, so 28. Right? Here, this one's a little bit different. I gave you the numbers. Let's write the isotopic symbol for it. So if this thing has 9 protons, what is the sample? What is it? Fluorine. It is fluorine, so we'll write that symbol. All right, fluorine. So what's missing here is the mass number. How do we get the mass number? Because I didn't give it to you. What is this mass number? 19, yes, because it's protons plus neutrons, so I'm going to put that 19 there, right? And then I would be done because this is charge neutral. You could put the 0 there, but again, if nothing is written in the corner, it implies it's a 0 charge. All right, so that one's all done. All right, next one. Let's do these two. These ones are ions. I'll keep those equations in there. So we got, oxygen and titanium. So I'll just do both of them at the same time. Oxygen has 8 protons. Titanium has how many protons? 22, great. All right, so neutrons come from mass number, so the oxygen must have how many neutrons? 8. How many neutrons on that titanium? 26, yes, okay. And now electrons, again, related to the charge. We already got the number of protons, all right? This is positive 8 coming from oxygen. So in order to get an overall -2 charge, how many electrons should I have? 10, yeah. So I'm going to add an additional 2 electrons because it has a -2 charge. But what about titanium? It has a +4 charge. So am I going to add more protons? No, we're going to just adjust that number of electrons to make that appropriate charge. So how many electrons should be there for titanium? 18, yes. So there's just 2 less electrons there, all right? Okay, then mass numbers, that's already given. 16 and 48. Perfect. All right. So there will be a question like this on the exam, okay? Because that's a very nice, like either multiple numerical input or something like that. So being able to read isotopic symbols. All right. So we saw earlier with this carbon example, here are 2 carbon atoms. They both have 6 protons, but they have different number of neutrons, all right? So can you really have an element with differing number of neutrons? Yes, you can, and they were able to prove like a sample of carbon is actually composed of isotopes that have different weights to them, different mass numbers. And we are able to adapt a experiment from J.J. Thomson to discover this. So how they discovered isotopes was they used something called a mass spectrometer. So the idea behind a mass spectrometer is we can take a sample and knock some electrons off of every atom in that sample. And so when you knock some electrons off, you produce a particle that's positively charged. And so if we put that positively charged particle through either an electric or a magnetic field, does that sound familiar? Yes. So if you put it through an electric or magnetic field, what happens through a mass spectrometer is that they're deflected at different rates. Or different deflections. So that's what you see right here. Put in a sample, irradiate them so you knock off an electron and send them through this magnet. And so what you'll see is if you have different isotopes with different weights, you get a splitting of these different isotopes with different weights. So we see that this chlorine atom with a 37 mass number and a positive charge is deflected less than this lighter chlorine atom with only a 35 mass number. But the idea here is, yeah, just put a charge on these atoms, send them through a magnet, they get deflected differently. And so we are able to collect the signals that come from here and deduce how much of your sample is each of these isotopes. So yeah, with a mass spectrometer, we can split up isotopes with different masses. And the spectrum that comes out of it looks something like this, all right? That if I put a pure chlorine sample into this mass spectrometer, some of the sample is chlorine 35, some of it is chlorine 37, all right? But based upon this graph, the signal is related to the abundance of each of those isotopes. Which of these isotopes is more abundant, the heavy one or the lighter one? The lighter one, yeah, the lighter one has basically 5 tick marks. And then this other chlorine sample, the heavier one, only has 1.5 tick marks, all right? Okay, so we see the majority of our sample is chlorine 35. So when we talk about the periodic table and the molar masses and the atomic masses on this periodic table, I'm not talking about the atomic number. The atomic number is the whole number, like 17 for chlorine. If you look under the chlorine atom, there's a number with a lot of decimal places in it. That is what we call the atomic number. That atomic number is the weighted average of all chlorine isotopes that are present in nature. Notice how, look at any element. Almost none of them are actual whole numbers. All of them are decimal places. Have decimal places there because many isotopes are present, and we have to take a weighted average. So what you'll see here is we're going to go through how to take a weighted average, where we're going to take those different abundances and apply them to the different masses of each of these isotopes. It's not just a simple 35 plus 37 divided by 2. We're not talking about equal weighted averages. Anytime you take an average, if you took a regular average of 35 and 37, what's the average? 36. But look at the periodic table for chlorine. Is its atomic mass 36? It's not. It's like 35 point something, 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 because the abundances are taken into account. So let's look at this. How much of this sample is chlorine 35? So we can use these tick marks to determine what is the abundances. So if chlorine 35 is 5 tick marks, how many total tick marks come from this sample? 6.5. So the fraction of your sample that's chlorine 35 is going to be 5 tick marks over 6.5, whatever that is. And then the rest of your sample is chlorine 37. So 1.5 tick marks over 6.5, the total. And so let's get those numbers real quick. So 5 divided by 6.5, that's about, I'm just gonna round this. I'm gonna say it's about 75% chlorine 35. It's pretty close to 75%. And then chlorine 37 is about 25%. Do you agree? We're just being very approximate right here. We're not actually doing this to precision, all right? That this sample is mostly chlorine 35 and about 25 of that sample is chlorine 37. So let's calculate a atomic mass, a weighted average based upon these numbers. So this is the last bit of math for midterm 2, or sorry, midterm 1. So this is the last bit of math for chapter 2. Nothing past this point has math, but this does have more math. So what we're going to do is calculate the average atomic mass of an entire chlorine sample, because never are we working with just a single chlorine atom. We're always working with billions and trillions of them. So what we want to do is have a mass that represents the average of all of them. And again, we're not talking about like the regular, even average, like a 35 and 37, its average is 36. That's assuming 50% contribution of both of those values. We just determined that chlorine 35, 75% of that sample is chlorine 35 and 25% is the heavier one. So we have to take into account that abundance. So here is the equation for your average mass. This is basically where you get the atomic mass that comes from our periodic table. So there's a lot going on here, but the idea here is you're going to sum up each of those isotopes that are present for your sample, where we're going to take the fractional abundance of your isotope and take the mass of that isotope, okay, multiply those two together, and then we're going to add up all isotopes that contribute to that sample. So if we were to do this for chlorine 35, if we wanted to calculate what is the atomic mass, or the weighted average, whatever, so we're going to actually use those abundances, what we would do, what we would put in our calculator is add up the product of the mass and the abundance for each of those isotopes. So here I have the percent abundance, but make sure when you put it into your calculator, you use the fractional type. So 75% as a fraction is 0.75. That's your fractional abundance. All right, 25% is 0.25. That's important because these are the numbers we're going to multiply together. I'm going to multiply that approximate mass of 35 AMU. AMU stands for atomic mass unit, and I'm going to multiply by that fraction. And I'll do the same for the heavier isotope and then add those two things together. So I'll show you exactly what I'm going to put in my calculator. I'm going to take care of the light isotope first, so 35 AMU times its fractional abundance, so 0.75. And then I'm going to add the other isotope. So that one is 37 AMU, and multiply by that fractional abundance, so 0.25. Right? So notice that this is not a exactly 50-50 average. We're taking the weighted average based upon the abundances that are there. And so when you calculate this, all right, so this is multiplication, so multiply these two things. So this first term is 26.25, and I'm going to add it to 37 times 0.25 is 9.25, right? I'm going to ignore sig figs because we're just doing an estimate here. I just estimated those abundances. This isn't like the true abundance. So if I add those two numbers up, so 26.25, I get a number like this, 35.5 AMU, right? That is the weighted average for this sample based upon the abundances that are there. What we see here is that this weighted average is closer to the lighter isotope because more of it is there, right? This is our weighted average, and if we look at the periodic table, someone tell me what is the atomic mass for chlorine, if you can read that small, because my eyes aren't very good. What does it say? 35 point what? 4, yeah, so 35.4. So, you know, our back of the envelope calculation, 35.5, really close to the actual atomic mass that is listed for chlorine, because again, all of those atomic masses represent the abundances of each of those elements of the isotopes that are stable in nature. All right, so yeah, again, the atomic mass we see is the average mass of all of the atoms of those elements as they're distributed in nature. They account for the different isotopes that are present. So here's an example, neon. Neon, a sample of neon. Most of those neons are like neon 20, all right? Neon with a mass number of 20. But there's a small fraction of neon atoms that are a little heavier than 20 AMU. And so a sample will have all of those distributed, but the the atomic number that we see there represents the weighted average of accounting for some of those heavier neon atoms. Yeah, that's what it looks like here. Most of your neons are neon 20. Some of them are neon 21, some of them are neon 22. So if we take the weighted average of this, we will see that 20.18 come out, all right, 20.18 AMU, because those slightly heavier isotopes are just pushing that weighted average a little bit further. It's really close to 20 because it's mostly neon 20, but yeah, those heavier isotopes just push it a little bit further. And yeah, so if you look at any of the elements and their atomic masses, you see that almost none of them are just even whole numbers, and the reason is because we are taking into account the isotopes that are actually there. So we call this fractional number the atomic mass, all right? We'll call this the atomic mass, and later in chapter 3 we'll call this the molar mass. This atomic mass has the unit of AMU, atomic mass unit. But yeah, later we'll call this molar mass. All right. So let's do some examples that are actually numerical. So lithium has two principal isotopes, lithium-6 and lithium-7. So here I give you the actual atomic masses for each of these. So notice that they're long fractions. So these atomic masses, isotopic masses, come from me weighing all of the protons, neutrons, and electrons, adding up that mass. All right, that's where those isotopic masses come from, the sum of the protons, neutrons, and electrons that are all present that you could figure out using that isotopic symbol. Notice that this is lithium-6. So those numbers, lithium-6, lithium-7, this represents the mass number. It is not the number of protons. Because I say the word lithium, you should know how many protons lithium has. It has 3. So the number that comes after the name is the mass number. So we actually know how many neutrons are there. So those are the isotopic masses, and here's one natural abundance. We learned in the previous slide, in order to do a weighted average, we need to know, how big are those peaks. I give you the natural abundance of one of them. I didn't give you the natural abundance of the second one. So does that mean we can't do this problem? No. What's the trick here? The two numbers there have to add up to 100. So yeah, I gave you 1. I told you that lithium-6 is, 7% abundance. That means the rest of the abundance has to be the other isotope. So this has to add up to 100%. And where's my calculator? So that means the natural abundance for lithium-7 is 100 minus 7.56. So this is 92.41%, right? Those are the percentages, but remember, we're going to be using the fractional form of this in our equation. So the fractions of these is going to be 0.0759 for lithium-6, and then the fraction for the second one is 0.9241. So how I got those fractions is I just took those percentages and divided by 100. Right, so these are the numbers I'm going to multiply. The atomic mass by the fraction, the isotopic mass by the fraction. The isotopic mass by the fraction, multiply them, add them up. So our atomic mass for an entire sample of lithium, actually, even before we answer this question, so let me just cover up what the answer is. Based upon the abundances, where is our atomic mass going to be closer to? Is it going to be closer to 6 or is it going to be closer to 7? 7, why? It's more abundant, yes. So let's just do the math and prove it to ourselves that our answer will be closer to 7. So I'm going to do 6.0151 AMU. This is the lithium-6 sample. Multiply by the fraction 0.0759. Add the contribution of lithium-7. So this is 7.016 AMU times 0.9241. Let's also do sig figs as well and make sure that we report to the appropriate number of sig figs. So we're doing multiplication first and then addition. So let's look at this. When I multiply these two numbers together, how many sig figs should my answer have? This number has 5 sig figs. The percent abundance has 3, so my answer should have 3, yes. Okay, so the answer that comes out of my calculator is 0.45654. I wrote a lot of numbers here, but the only significant ones are the first 3. So 3 decimal places, but I'm not going to round yet because I'm not done yet. And then I'm going to add the second one. So if we do multiplication here, 4 sig figs, 4 sig figs, how many sig figs in my answer? 4. And so you put this in your calculator, it's 6.48348. So only these 4 first digits are significant. All right, next we do addition. So do I count my sig figs? No, what do? You look at place values. Yes, so this first number goes out to 3 decimal places. The second number also goes out to 3 decimal places. So my answer is going to go out to 3 decimal places. Perfect. So never did I count a sig fig. I just looked at the place values. So that means I should be able to report this answer to 3 decimal places. So that number plus 0.45654. Okay, that is not right. Okay, 6.48348 plus 0.45654. I get 6.94002. That's what comes out of my calculator. But like I said, we're going to go out to 3 decimal places because it's addition. So 6.40, whoops, I forgot the 9. 6.940 AMU will be my answer out to that 3rd decimal place. And that's the answer in the corner as well. Right? So that's the appropriate weighted average for a lithium sample. And we were right that this answer is closer to 7 than it is to 9. Because you would know like a regular average between 6 and 7 is 6.5, but this isn't an exact 50-50 distribution of this sample. Now let's check our sample. Where is this number important? 6.9 whatever. Well, where will we find that number? 6.94. On the periodic table. Look at your periodic table. What does it say for lithium? 6.94, I think 1. So we're just off a little bit at the last sig fig. So we just calculated the atomic mass that comes from our periodic table. All right, let's do a harder one. So notice here, the math isn't too bad. Okay, the math isn't too bad. As long as you have your isotopic masses, your percent abundances, then you're good. Well, we can rearrange this question, all right, and give you a different, have you solve for a different variable, right? Here we solve for atomic mass, so we just, put all the numbers together, solve for atomic mass. But I could ask you by, giving you more information and leaving out a piece of information, we could solve for different variables, and that's like the second question. Boron has 2 isotopes. Here are the masses of those 2 isotopes, boron 10, boron 11. I tell you that the periodic lists an atomic mass for boron is 10.8 AMU. What is the natural abundance of each of these isotopes? All right, so basically in the last question, I gave you the full table. We calculated your atomic mass. In this question, I give you the atomic mass. We are going to solve for the natural abundance. But we have a problem here, okay? Because there's a, if we kind of like try to, abundance, if we try to like fill in this table, I don't know what the abundance of boron 10 is, and I don't know what the abundance of boron 11 is, right? So if I called these variables like x and y, can you solve an equation that has 2 variables in it with one equation? Wait, two variables, 1 equation. Can you do that? No, you can't. So we have to come up with a trick, all right? We have 2 variables, 2 different numbers we're trying to solve for, the abundance of the light isotope and the abundance of the heavier isotope. So we have to invoke a trick again. What's special about the variables x and y? They have to add up to 100%, yeah. They have to add up to 100%. So for example, if x was 40%, you just have to solve for x, because if you know x is 40%, we already know that y has to be 60%. So we're going to invoke that trick again, where we know x plus y equals 100%. But I'm going to say that this is equal to 1 because I want to work with fractions, because our equation is going to work with fractions, right? So we can invoke a second trick, because right now, if I put together an equation with 2 variables in it, I can't solve for it. So I need to simplify this so it just has 1 variable. So I'm going to rearrange this equation, that says that x plus y equals 100%. and say, oh, y is equal to 1 minus x. Do you agree with that? Yeah. Okay. And look, if I shove that into this table, y equals 1 minus x, I can put together an equation that actually only has one variable. All right, so let's put this together. All right, so the equation we're going to do is just like we set up the previous one. It's just now we're putting our variables in a different place. Basically, when we multiply our isotopic mass by our abundances, we're going to do the same thing here. Multiply these two numbers, add them up. But this time I already know what it's equal to. So 10.811 AMU is equal to the yellow numbers multiplied together, so 10.013 AMU X. I'm just going to get rid of units. It's all in AMU. And then I'm going to add, so this is boron 10, and then this is the contribution of boron 11. This is 11.009 multiplied by the abundance, so 1 minus X. This was the Y that we had earlier, all right, but we simplified it. And so now we solve for it, because how many variables are in here? Just one x. But we just need to combine them all so we can solve for it. So this is just algebra, but I'll show you the steps. To combine the x terms, I'm going to distribute that 11.009. So if you distribute that, this equation becomes 10.811. I'm going to get rid of units. 10.013x plus 11.009 minus 11.009x. Now we combine all of our terms. So I'm going to subtract 11.009 from both sides, right? Put all of those constants on one side, and then I'm going to combine these two x terms at the same time. So if I subtract that 11.009, I get negative 0.198 equals, if you, we're subtracting 10x minus 11x. So this becomes negative 0.996x. That is something we can solve, right? That's just an x term. So what are we going to do to solve for x? Divide both sides by negative 0.996. And what kind of number comes out? A positive or a negative number? Positive, yes. It's a negative divided by a negative, right? So it does end up being positive. All right, and so what we get is that x equals 0.1988. Okay, so what does that mean? Is that our answer? It can't just be our answer. We have to understand what this number means. It's a percent abundance, or I guess it's a fractional abundance, right? It's 19, this means 19.88%. But it's the percentage of what? Boron, which boron? 10, it's the first one, boron 10, because we said that boron 10 was, its abundance was X, so this is the abundance of boron 10. So do we have to do this again to get the abundance of boron 11? No, we just have to recognize, oh, the rest of the sample is going to be boron 11. That's that Y term, and it's 80%, right? All right, and so that's how you do, that's another way to, work that equation. I will say that that one's harder. That one's harder, but you can do it. When there's an abundance missing, recognize that all of the abundance added up together, plus that missing piece has to add up to 100%. All right, here's a conceptual exam question. All right, I literally stole this from a previous exam. All right, in nature, magnesium consists of 3 isotopes. A sample of magnesium was measured using a mass spectrometer. Which of these spectra best represents a sample of magnesium? So remember, the heights of the graph on our mass spectrum is related to the percent abundance of our sample. By looking at the heights of the graph, you can kind of estimate where is that weighted average going to lie, right? So let's eliminate one of the graphs right off the bat. What is the first statement in this question? In nature, magnesium consists of 3 isotopes. So which one of these graphs is wrong? D. Why? There's only one isotope. Yeah, so D is incorrect. So now we have 3 other graphs with a bunch of different lines on them. How do we know which one's right? So there's a piece of information missing. I see a lot of eyes going to the periodic table. What is important on the periodic table right here? Magnesium's what? It's atomic mass. So which number are we going to use? The 12? We're going to use the 24.3. All right, we know that the atomic mass of magnesium is 24.3 AMU. So that number is the weighted average. We're looking for the graph where it has a weighted average close to 24.3. So if a student selected D, they were right that, oh yeah, that peak shows up at 24.3, doesn't it? Doesn't that peak show up at 24.3? But what did they get wrong? They didn't account for the 3 isotopes that we have to actually calculate the weighted average to get 24.3. D is wrong because it has not enough isotopes. Okay, so which one of these graphs has its weighted average as close to 24.3 as possible? We can kind of estimate what they are. Let's go work backwards. See, where will its weighted average lie? At 25. Yeah, this is actually just an equal average, right? An equal average. So yeah, this has a weighted average about 25. B has a weighted average where? Also 25. And then A is the only one that has a weighted average just a tick, above 24. So this one is probably the one that is closest to 24.3. So the answer is A, right? Okay, good. So you didn't even have to do any math. We can just kind of inspect by the heights of the peaks. We recognize, oh, in A, most of your sample is 24 AMU, but with a couple of heavier isotopes, it just pushes it a little, that weighted average a little bit higher to 24.3. And so that's why we see a lot of elements up here with atomic masses that are close to a whole number, but like a couple decimal places at the end, because a couple heavy isotopes just bring up that weighted average a little bit. All right. Okay, so that is our atoms. Yeah, so that's the last mathy part of the chapter. I guarantee you there will be some type of weighted average atomic mass question on the exam. You might have to calculate it, or it could be conceptual like this, understanding how to read a mass spectrum and assess weighted averages from it. All right, got 30 more minutes, so let's talk about the periodic table, talk about the elements, because we just looked at isotopic symbols, so let's inspect the different parts of the periodic table and how else can it be useful for us. All right, so I do hope that you're working through the annotated slides because I have all of this already filled in for you of what you need to know off the periodic table. So again, you will always be given a periodic table on the exams, but what piece of information is missing from it? Names. That is the only thing that is missing. You don't have to memorize atomic numbers. You don't have to memorize masses, atomic masses, but you do need to know that potassium is what symbol? K, because then once you know that piece of information, then that unlocks, oh, potassium has 19 protons. It has a mass number of blah, or an atomic number of blah. So that's what you need to know. Right? So what else off the periodic table you need to know? Not just the element names, but the different regions of the periodic table, all right? Know the difference between a group and a period. A group is a column, all right? A column of elements. So right here, I'll highlight it, right here, pink, all right? A group is a column of elements. So our groups are numbered by number. So group 1A, 2A, 3A, things like that, right? What we see is that elements in the same group tend to have similar properties. Similar properties. That's what we typically see. Right? It's called group chemistry. Right? So all, like lithium, sodium, and potassium, they have similar properties. All of them are kind of explodey when you put them in water. But compare, lithium to chlorine, different properties because they're not in the same group. Right? So we got groups, those are columns, and then periods are our rows of elements. So like potassium and calcium, they're in the same period because they're in the same row. Know our main group elements. So those elements are the elements in groups 1A, 2A. Notice that we skip over our, these are called our transition metals. They have the B designations in their groups. So 1A, 2A, then 3A actually starts over here, all the way to 8A, All right, so our main group elements are basically the edges of our periodic table. The transition metals are in the middle. And then finally, the most important thing off this periodic table to know is your metals, your nonmetals, and your semi-metals. So there's a trend here. Metals are on the left side of your periodic table. Your nonmetals meaning not a metal, are on your right side of your periodic table, where this line separates them. All right, so here are your nonmetals, here are your metals, where these highlighted yellow elements, those are called your semi-metals, or sometimes they're called metalloids. So they're not quite a metal, they're not quite a non-metal, they're somewhere in between. Sometimes they take on metallic characteristics, sometimes non-metallic. So they're in the middle because they're right between, they're sandwiched between the regions of where you find metals and where you find semi-metals. So this is something that you need to memorize, and that isn't on your periodic table, is off of this like stair-step line, which ones of these elements are semi-metals. So I always remember it's boron first, and then it's like 2 sets of 2 as a staircase. So boron is a semi-metal, silicon, germanium, arsenic, antimony, tellurium, polonium are semi-metals. Everything on this side are non-metals. Over here, they are metals. Perfect, okay. What else do you need to know? Some of the common group names. So 1A is an alkali metal, so do know that name. If I say, okay, like name an alkali metal, you just list any 1A element metal. Alkaline earth metals is 2A. Other common names are noble gases, which is 8A elements, and 7A is halogens right here. Those are common names. If you look at very, very old textbooks, 6A elements are often called chalcogens, but I haven't met anyone who's alive who still uses that word. So yeah, but yeah, these are the common ones, 1A, 2A, 7A, and 8A. All right, and the last thing here is hydrogen is special. Because look, hydrogen's right here. It's above lithium. It's above lithium. So you would think that hydrogen and lithium have similar properties, right? Because lithium and hydrogen, they're in the same group. So they should have similar properties. But hydrogen is special because it's along with the metals, but it actually behaves as a non-metal. So really, if you look closely at this periodic table, it's really weird. The one that's on the screen, not the one that's on the board. This one's weird because hydrogen's right here on this periodic table on the screen. But look, hydrogen's also over here. See how it's showing up in 2 places? Because hydrogen acts as a non-metal. So really it belongs over here with its non-metal friends, but because of its electron configuration, typically it's over here. So just do memorize that hydrogen, even though it lives off with the metals on the periodic table, it behaves like a non-metal. All right, so that's what you need to know off the periodic table. So let's practice a little bit. Let's name a halogen in period 5. So periods, they start from the top. So you start out period 1 with like hydrogen and helium, and you work your way down. So halogen means what? 7A, all right? So we are looking at group 7A. We're going to count down. 1, 2, 3, 4, 5. So this is iodine. All right, I'll write it out. Iodine, iodine. Okay, name an alkali metal in period 3. What does alkali metal mean? 1A, yeah. So we're going to count off of 1A, period 3. So hydrogen's period 1, 2, 3. So this is sodium, Na, sodium. Right. Alkaline earth metal in period 4. That is group what? 2A. So period 4. So we're looking at group 2A, period 4. So beryllium, this starts which period? Is it period 1? Nope, that's period 2 because hydrogen starts at period 1. So it's 1, 2, 3, 4. So this is calcium. All right, and the last one, noble gas in period 2. Just yell it out. Neon, yay, okay. Name 2 group 5A metalloids. So we look at this graph. We know 5A is right here. So we are looking at this column. That's 5A, but which one of these elements are metalloids? Phosphorus and arsenic, are we sure? No. Yeah, so let's just highlight the ones that are metalloids. Boron is a metalloid. Then it goes silicon and germanium. arsenic and antimony, tellurium, polonium. So the answer is actually arsenic and antimony. Let's make big mistakes, because then we remember our mistakes and we don't make them again. So arsenic and antimony, so Sb. But you know for a fact that nitrogen and phosphorus would also be options if this was a multiple choice exam, because we recognize, you know, you guys can count 5A and recognize, yes, 5A, but which ones are the metalloids? That's the tricky one. All right, name a group 4A nonmetal. So we're going to look at the nonmetals, group 4A, so you can count. There's 4A. I already have it highlighted for you. So where is our 4A nonmetal? Which one? Carbon. Is there any more nonmetals in group 4A? Nope, it's just carbon. The rest are semimetals or metals, so it's just carbon. Which element is most likely to have similar properties to oxygen? So let's highlight where oxygen is. Oxygen is right here. So which one? Nitrogen, fluorine, or sulfur? Which one will have most similar properties to oxygen? Sulfur, yeah, so the tricky thing here is all of these elements, they just butt up right next to oxygen, so I just picked the three that are around it. But the idea here is that elements in the same groups tend to have similar properties. All right, which element is most likely to have similar properties to germanium? So let's highlight germanium, it's right here. So germanium's there, and what are our options? Gallium, carbon, or arsenic? Which one will have more similar properties to germanium? Carbon, we think carbon. You might think carbon because germanium and carbon, they're in the same group, they're in the same column, but what's the problem with carbon? What kind of element is carbon? Non-metal. What kind of element is germanium? A semi-metal, yeah, it's one of the highlighted ones. So let's reconsider that answer. It's actually, the correct answer is arsenic, because both of them are nonmetals, right? Both of them are nonmetals. Let's see, nonmetals. Yeah, so our answer here is, yeah, germanium, or no, I just circled germanium. Arsenic, yes, because they are both nonmetals, or sorry, semimetals. Semimetals, okay? Yes, I chose two things that are in different, chose two things in different columns, but we also have to consider what kind of element is it? Is it a metal, or is it a non-metal, or is it a semi-metal? So do consider that, that as well. I'm trying to think off my head like another example, but I can't right now. All right, so there's an example. All right. So let's, okay, use the periodic table to start naming things. So know the numbering system. We're going to use it a lot for naming. All right, ions. We talked about elements when they're charge neutral. Like if I'm talking about a carbon atom, it's charge neutral. So a charge neutral carbon atom has 6 protons, 6 electrons. But when we work with samples, you know, in lab, the atoms that are composed of our samples are not always charge neutral. Sometimes we are working with particles that are ionic or made of ions. So we're just going to dive deeper into the idea that, you know, the number of protons and electrons don't always have to match, and we can have something that's an ion, or the overall particle is charged. And so here's the nomenclature for ions. When things are charged, they can either have a positive or a negative charge. So in general, when we talk about things that are negatively charged, we call those anions. So anions have more electrons than they do protons in order to get that negative charge. Cations, on the other hand, these things tend to lose electrons, so they end up with that positive charge, all right? So both of these just mean ionic or ions, and the name just indicates is it positive or negative. So I just remember cation, a T looks like a plus sign. So cations are positively charged. And then I just remember anions are the other one. All right, so I just remember cations has a T, so it's positively charged. And what we'll learn here is that a lot of the elements have very predictable charges, and I've written that trick up here, all right? Cations are typically going to be metals. Metals, typically lose electrons to form cations where the charge equals the group number. I have this on another slide too. And then anions, when talking about just the elements, monoatomic ions, these are typically nonmetals where the charge is the group number -8. And I have that on the next slide, right? We can predict most monoatomic ion charges using the periodic table. So what's boxed right now, those red elements, those are our main group elements. Those are our 1A, 2A, 3A, etc. elements. Those different columns, we're skipping over the transition metals for a reason. So these main group elements have very, very predictable charges, all right? Where all group 1A elements, all of these metals, when they are an ion, always form a +1 charge. So this is just something that does need to be memorized, I guess, but all the trends just come from the periodic table, all right? If I'm talking about a lithium cation, it's going to be a +1 charge. If I'm talking about a rubidium cation, it's going to be a +1 charge because it's a group 1A element. Or calcium will always be a 2+ charge because it's in group 2A. So yes, you need to memorize this, but you don't have to memorize them individually, right? You just have to know, oh, if I'm talking about a magnesium ion, what charge is magnesium going to have? +2. You don't memorize that. You memorize, oh, magnesium is in group 2A, so it's going to adopt a +2 charge. So those are cations. The name of these cations is just the element name and the ion, and the word ion. So if I'm talking about a charge-neutral calcium atom, I say calcium atom. But if I'm talking about the calcium 2+, I just call it calcium ion instead, right? On the other side, our nonmetals over here, this is where we get our anions. Remember, the trick here is that it's the group number -8, all right? So what we see here, first, noble gases, group 8A, very rarely make ionic compounds. That's why it's missing here. But what we see here is that group 7A elements always adopt -1 charges. Group 6A always adopt -2 charges. Group 5A always adopt -3 charges. If we had a group 4A anion, what charge do you think it would adopt? -4, yes, if we go along with that trend. And so those numbers come from this idea. It's group number -8, all right? So fluorine, chloride, bromide, iodide always have a -1 charge as an ion. Oxygen, so oxide, sulfide, always have -2, and etc. Naming for anions are a little bit different, okay? It's the monoatomic anion name with the element base name with the ending "ide." And I'll talk about this a little bit later. I just want to introduce it right now. Where if I'm talking about an oxygen atom, I say oxygen atom, that's charge neutral. But if I'm talking about oxygen with a 2- charge, I don't say oxygen ion. No, I call it an oxide ion, all right? So anions always have the "ide" ending, right? So let's go through these examples. Yes. Yeah, we just said that everything in this group, all the nonmetals here, would be a -4 if carbon was in a ionic, right? Okay. Yes, all right, so let's go through these examples, all right? So sodium and aluminum, those two are metals. What's the charge of sodium going to be if it's an ion? +1, because it's in group 1. What about aluminum? +3, yeah, because it's in group 3 and it's a metal, all right? And the names of these, this is sodium ion. And then aluminum would have the name aluminum ion. All right, okay. So these other ones, so we did, calcium 2+, that's the calcium ion. Calcium's in group 2A. Oxygen is a 2- because it's in group 6A. We call that the oxide ion. So what about chlorine? What would its charge be if it's an ion? -1. Did you memorize that? No, I hope not. You just recognize it's in group 7A. All 7As are a -1 charge. What would the name of that be? Chloride. Yes, chloride ion. All right, nitrogen. Nitrogen. Don't look at the table, look at the periodic table. Nitrogen's going to adopt what charge? -3, yeah. So this name would be what? Nitride. Yes, nitride ion. Okay, there we go. So those are our monoatomic names, So notice that this works very well for everything that's in these nonmetals and group 1A and 2A metals. So what I skipped over are kind of these elements in the middle. These are what we call variable charge cations, all right? These are a little harder to predict, right? They're a little bit harder to predict, so when we write out the names of these, any metals present here that are ionic, we have to tell the reader exactly what the charge is, because those elements in the middle can have variable charge. Like if I say chromium ion, well, chromium can be a +3 or a +6. So I have to clarify to the reader which type of chromium I'm talking about. So in order to clarify what that charge is, we use a Roman numeral system. It's called the stock system. I love the stock system because I don't even have to look at the periodic table, all right? Iron with a Roman numeral 3 means I'm talking about an iron atom with a an iron ion with a +3 charge. Or if I'm talking about copper 1, that means copper has a +1 charge versus copper 2 Roman numeral, that means copper has a 2+ charge, right? So the idea here is that these elements in the middle can adopt different charges. It's not predictable like our main group elements, so we have to tell the reader exactly what those charges are. So if we go through these, all right, iron 3 refers to an iron 3+ cation. Copper 1 refers to a copper +1 cation. Copper 2 is different, it's copper 2+. Right? But the hard part is going the other way. So recognize cobalt 2+ here. Yes, cobalt has a 2+, but it is an element kind of in the middle here of our periodic table. So we have to use the stock system if we're writing its name. We have to use the stock system to tell the reader exactly what we're talking about. This is cobalt 2. We can't just say cobalt when writing the name. Sn, what element's that? Tin, that is tin. Can we just write tin ion? Nope, we gotta say tin 4 because tin can adopt different charges. It could be tin 2, tin 4, gotta tell the reader what it is. And the last one, what's that? Gold, yeah, so this is gold 3 because gold 1 also exists. Gotta tell the reader what it is, right? So everything highlighted here is variable charge, so I like to just remember it's everything in the middle of the periodic table except for a few things. All right, the elements silver, zinc, and aluminum, they're in the middle of the periodic table, but these elements also have fixed charges, all right? So silver, when it's an ion, is always silver plus. So since it's always silver plus, we do not need the Roman numeral when talking about a silver ion because it's only ever silver plus. We don't have to say silver 1, that's redundant. Zinc also, same idea. Zinc 2+, it's always a 2+ ion, so we don't actually have to say zinc 2 Roman numeral because it's always 2+. And same thing for aluminum. Aluminum is always 3+ as an ion, so you don't have to use Roman numerals there. So those 3 are the exceptions. Yes. Can have variable charges, yes, everything highlighted. So all of the elements in our non-metal group right here and all the metals, metals right here are fixed charge. Yeah. So sorry, I did not mean these ones right here. So I'm just talking about right here. And so notice it says in general main group does. So what I'm referring to are these non-metals have fixed charge, these metals have fixed charge, but all of these other blue metals, so let me just put it in pink, all of these have variable charges. Yes, some semi-metals also, yes. Yes. Yes, our semi-metals do also have variable charge as well. All right, so we'll do some examples in a little bit. All right, so you guys memorize these polyatomic ions already, right? Yes, I hope you did. Because I'm not going through them. You are required to know these. If I say ammonium, you need to know the formula of ammonium. What is that? NH4 plus you need to know the charge, so it's NH4 plus, and you need to know the name, ammonium. Carbonate is what? CO3, what charge? 2 minus, always CO3, 2 minus. Nitrate is NO3 minus. So here are some tricks though. So you'll notice there's nitrate, sulfate, phosphate, chlorate, those things. There's some tricks for anything with oxygens in it, and here are the tricks. We can talk about sulfate, SO4 2 minus, but if we start adding or removing oxygens from that formula, it's called an oxyanion. There's some rules, okay? So notice how a lot of these end in the 8 ending, like 8 ion. So the tricks for oxyanions is if you start adding or removing oxygens, it follows a certain form, all right? So identify the nonmetal, so X that's in your oxyanion, that's kind of like your base name, like sulf in sulfate or nitr in nitrate. If you add an extra oxygen to the regular formula, add the per fixing and add the 8 ending. But if you take away an oxygen, change the 8 ending to an ite ending instead. And if there's 2 less oxygens, keep that ite ending and add an hypo prefix. So these pre and suffixes on these ions are related to the number of oxygens that there are relative to the reference or like the regular oxyanion. Note that the charge of the oxyanion will never change. So let's just look through some examples. I think it's better to know the examples. So my strategy here is do memorize sulfate, chlorate, nitrate. Remember those ones, the regular 8 endings, and recognize if you adjust the number of oxygens, then apply that oxygen name changing tip. So the idea, let's just go do these examples. NO3 minus, what do we call that? Nitrate, that's the one you should memorize. But NO2 minus, what is that? Nitrite, yes, do you memorize that? I mean, you can, but I recognize, oh, NO2, that's 1 less oxygen than the regular NO3. I memorize nitrate, and I just remember the oxygen tip. Take away an oxygen, it turns into an ite ending. Notice how it's still negative charge. All right, SO4 2 minus, what do we call that? Sulfate, yes. So what does that make SO3 2 minus? Sulfite, because it is 1 less oxygen. All right, let's do all these chlorines. What is ClO3 minus? Chlorate. Yes, that's the regular one you should memorize. So notice that the rest of the chlorines in this examples are just differing amounts of oxygens. So here we add an oxygen. So what do we do to the name? Add the per. So this is perchlorate, right? So ClO2, so if we go back to chlorate, we are losing an oxygen. So what is that name? Chlorite, yes. Right, and now finally, we lost 2 oxygens relative to where we started. So this is going to be hypochlorite. Notice how all of them have the exact same charge. All right, so that's some practice. All right, so let's write some ionic formulas, okay? Remember, these things are ions and have to be charge neutral. We're combining things that are positively charged, negatively charged, so we have to combine them in such a way to ensure that they're charge neutral, right? So like here's an example, aluminum 3+ combined with oxygen 2-. We can't just do a 1-to-1 ratio to make it charge neutral. In order to make the whole substance charge neutral, I have to have 2 aluminum 3+ and 3 oxygen 2-. That gives a +6 and -6 to both sides. Use subscripts to denote how many of each ion there are. So let's just do some practice in combining positive and negative things to ensure they're charge neutral. What ionic compound? Write the full ionic compound when you form it between magnesium and fluorine ions. So how many magnesiums are in my formula? 2? 1. How many fluorines are there? Fluorides? 2. Yes. So the idea here is if I have a +2 coming from magnesium, I need 2 anions to make that charge neutral, 2 fluorines. So that's why it's called MgF2. There are 2 things that are -1, 1 thing that's +2. Overall, that's charge neutral. All right. So let's do these other ones. Barium and carbonate, what's the ratio there? That one's just 1 to 1. So we just write BaCO3, 1 to 1, because a +2 -2, boom, charge neutral. The next one, ammonium phosphate. What's the ratio there? How many cations do I need? 3, and then how many anions? 1. Yeah, so this is going to be NH4. I'm going to write that whole thing in parentheses and put a 3 and put phosphate at the end there, all right? So we have 3 things that are +1, 1 thing that's -3, so it's charge neutral. And then the last one, I already did that one. So notice that it's aluminum 3+, oxygen 2+. So if I have 2 aluminums and 3 oxygens, both of them will contribute a +9, a +6 and -6. So it'll be Al2, oh my gosh, 2O3. Yes. PO4. Yes, it would be. Very good. Carry 4, PO4. Thank you. Okay. All right, so that's forming ionic compounds if you know the charges already. All right. I still got 5 minutes, right? Yes, still got 5 minutes, an 80-minute class, yes. The past couple days I've been ending 5 minutes early, and I didn't know it, so we need that time. All right, so let's talk about naming ionic compounds. We're gonna learn 3 different naming schemes, and the idea here is you first need to recognize, if I give you a compound, recognize, is it an ionic compound or is it a molecular compound? Because they have different naming rules. So we're gonna learn ionic compounds first. Ionic things are made of ions. So if there's ions present, you're gonna use ionic naming rules. And the other tip is typically, when talking about ions, it usually is composed of a metal, usually metal and a non-metal. Not always, but if it's a metal and a non-metal, sure enough, you're gonna use ionic naming rules. So here's the basic rule, all right, is when you're given an ionic compound, name the cation, then name the anion. That's it. Never, ever, ever use prefixes to denote how many of each ion there is. You just name the cation, name the anion. That's it. But remember, cations sometimes can have variable charge, so you might have to use the stock system. And for anions, that base name has the "ide" ending, right? So we just name the cation, then the anion. That's it. That's how you name ionic compounds. So this first one, MgCl2, should I call this magnesium dichloride? No, you should not. All you call this is magnesium chloride. That's it. So notice that the anion does have the "ide" ending. I don't say magnesium chlorine, it's magnesium chloride, because anions will always get that "ide" ending if it's monoatomic, right? Let's do the ones that aren't starred first. So is this dipotassium sulfide? It is not. It is just potassium sulfide. That's it. Okay, what about this one? The one on the bottom? That is called, what is NH4? Ammonium. So this is ammonium. And then what's the other thing? Sulfite. So notice I did not put I didn't put 2 ammoniums. No, I just said ammonium sulfate. And then the last one that's not starred, NaClO. Sodium, what is that? It's on the previous slide. ClO. This is hypochlorite. Okay, that's it. Whoops, sorry, chlorite. All right, so the reason these 2 are starred, notice that magnesium, potassium, sodium, ammonium, can you predict the charges of those things? Yes. So those cations, we know the charges of them, so we don't have to tell the reader what the charge is. But the middle ones, iron, can we predict the charge of iron off the periodic table? Nope. Can we predict the charge of chromium? Nope. So we have to tell the reader exactly what that charge is. So how we determine that is to back calculate it, all right? So oxygen typically has a -2 charge. So that means based upon the number of irons that are there, this is a +3 charge. So we're going to call this iron 3 oxide. So what would that charge of chromium be for the second one? Nitrate always has what charge? -1. There's 2 of them there, so what charge is chromium? 2+. So this is called chromium 2 nitrate. And so those ones are special, all right? So we'll end right there. Do practice with naming. Do memorize all of those polyatomics as soon as possible by our exam next week. And we'll practice more of these on Thursday. We may start chapter 3 on Thursday as well.